Hey guys, in this video I'm going to show you a couple examples of finding the gradient of a three-dimensional function or a function of three variables, x, y, and z. This is my friend over here who's always happy, see? So you've got to be two. There you go. Let's take a look. So the function is the following. So f of the variables x, y, and z. So f is the function, the variables are x, y, and z, is given by the following rule. X squared plus y minus z squared plus z times ln of x. Okay, so this is our function, x squared plus y minus z squared plus z times ln of x. And we will find the gradient. We need to find the gradient of the function here at the point 1, comma 1, comma 1. So the point 1, 1 in three-dimensional space. So of course all you need to compute are the partial derivatives of this function with respect to each of the variables. So let's do that right now. So f sub x, right? So the partial with respect to x is given by 2x. That goes away, that goes away. With respect to x, these are constants, so they differentiate away, they do not vary. There you go. And then z times ln of x, well, you simply keep the z because that's a constant. And the derivative of ln of x is just 1 over x, so you write it this way. So 2x plus z over x is the partial with respect to x. With respect to y, the partial is the following. That goes away, that's your 1, and that's it. Everything else goes away, see? This doesn't vary with respect to y, nor does this, nor does this. So the partial with respect to y is very nice here. It's just a constant 1. Easy. And then the last partial here will be with respect to z. So f sub z. Okay, and that one has the following form. You differentiate this, so we'll give you negative 2z. And then the z differentiates away from this term, and all that remains is plus ln of x. So these are the partials of our function. Okay? And now we just plug them into the definition of the gradient, which tells us the following, that the gradient of a function like this is given by, remember this is a function of x, y, and z, the spatial coordinates, little point in space. So in other words, as you move from one point to another point, this thing changes. Alright, so what we have is the following. We need, by definition, this quantity, then we need that quantity, and the last one is that one, right? So you're plugging the partials into the components of this. So let's do that right now. F sub x is 2x plus z over x. So this is our I component. And we add to this the j component, which is just, in this case, very nicely 1j, and then we add to this the k component, which is very nicely negative 2z plus ln of x. And this is the component in that direction. So this is the gradient vector for any value of x, y, and z, right? You see it's all in terms of x, y, and z. And now at this step, what we will do is, and keep smiling, it's multivariable calculus, you've made it this far. That is a reason to give yourself some credit. So, take a look. Let's evaluate this at the point 1, 1, 1. So all we are going to do is plug in 1, comma 1, comma 1 equals 2 times 1 Let me color code this, right? So you see it. It's 2 times the 1 here, plus, and the z will is replaced, and the x is once again replaced, and this is our I component. Plus, now the y component is constant, so we got lucky with that one. We just keep it as 1j. And the last one now is this. So you have negative 2 times the 1 plus ln times the 1, like this, okay? So you have to simplify this. In other words, you're simply replacing x, y, and z with 1, 1, and 1. The rest of it is simplification, so you've got 2 times 1, which is 2. 1 over 1 is 1, so 2 plus 1 is 3. So you end up with 3i, of course, plus 1j, that doesn't change. And now this last part is the following. You've got your negative 2i plus the ln of 1, which is like saying e raised to what number is 1? That number is 0. So ln of 1 is 0. So what we have lastly is just minus 2k. So this vector represents the value of the gradient at the point 1, 1, 1 for the function given by this. And that is the procedure. It is fairly elaborate, but it's multivariable calculus. But you do it a few times, and it's elaborate but mechanical. Think of it that way, right? So you've got a function, you differentiate, plug into the definition of the gradient, and then evaluate the gradient at a given point, and out pops a vector that is the gradient at that point. And that is it. So thank you for watching.